the repeated squaring technique. I show you a simple example last time. And here, at this point, I need to prepare you for our first programming project. This part included repeated squaring, repeated cubing, related to our first programming project. Other than Horner's rule, we just learned Horner's rule last time. So we need to learn two more improvement techniques here. All right, so let me also get the, yeah. All right. Yeah. So what's that? Repeated squaring. Repeated squaring technique. So here, our goal, we want to evaluate monomials efficiently. So it's a special case. So it's not a general case. General, that's the polynomial case. Here we only consider monomial. So monomial, x to the kth, that power function. No coefficient. Only x to the kth, that simple function. So the question, what is the fastest way to calculate a monomial given x and k? How to calculate this expression, x to the nth here, x to the nth, in the fastest possible way. So here I introduce two techniques, repeated squaring and repeated cubing. All right. First, repeated squaring. All right. What do we have so far? When we start, let's look at the Horner's rule first. Horner's rule, we calculate this monomial directly, because monomial is just a special case of the polynomial. So all these terms 0, only the last term non-zero, and the leading coefficient is 1. A sub n equals 1. All the other coefficients are 0. In that case, now, so here, the question. When we calculate this polynomial for the general coefficients, general arbitrary given coefficients, A coefficients, then Horner's rule is the best for the general coefficients. But for special coefficients, Horner's rule may not be the best. Special coefficients. And our monomial case, special coefficients. Horner's rule may not be the best. Here, I want to show you. We can do much better than the Horner's rule here. All right. The special case. Can we do better in certain special cases? Here, let's consider a few special cases. Yeah. All right. Look at we did this before. Remember the last time we only need 2 multiplications. If we do Horner's rule, we need 3 multiplications. Remember k minus 1. With the coefficient 1, because we don't need a multiplication related to the coefficient. So we need 3. Repeated squaring, we only need 2 multiplications. That's a simple example. Now, we want to apply the technique we used here a few more times. So let me show you how to apply that special technique several times. The first time, x times x equals x squared. First time, okay? Second time, x squared times x squared equals x to the 4th. All right. Can we keep doing, so here we call this technique repeated squaring. Yeah. Can we keep doing this again and again if the exponent number n is power of 2, 2 to the kth power, okay? In that case, every time we take square of the current number, current intermediate result. Yeah, let's call this intermediate result. Okay, all right. So let me use this little chart to do experiments. Okay, so the first column, K column, the second column, monomial column, corresponding monomial column. All right. Number of multiplications. Yeah. Counting numbers, the third column. Yeah. So let's do our experiments here. When k equals 1, yeah, n is 2 to the first, right? K equals 1 square. Yeah. X squared, the multiplication we need 1. Yeah. X times x, 1. Yeah. Next one, k equals 2. We want to calculate x to the 4th, so we need one more multiplication, 2. Yeah. One more square, so that's why one more multiplication, and so on. That's 3 x to the 8th and 3 multiplications. Yeah. Keep doing for general k, x to the 2 to the kth, k multiplications. Yeah. See? Yeah, here. Conclusion. Yeah. So if we apply this repeated squaring technique, yeah. If k equals 10, yeah. K equals 10, yeah. And 2 to the 10th, yeah. 2 to the 10th, yeah. That's 1024. 2 to the 10th, 1024. Okay? Yeah, here. You can see. When we calculate this monomial, x to the 1024, we only need 10 multiplications. How about that? How fast it is. If you compare it with Horner's rule, if we do not use this repeated squaring, we just apply Horner's rule. If you calculate x to the 1024, how many multiplications do you need? 1023. Just one fewer, k minus 1. One fewer, because you do not need to consider leading coefficient. Leading coefficient is 1. So that multiplication can be saved. You only save 1, so 1023. See the huge difference. This technique, you only need 10 multiplications. That one, Horner's rule, 1023. How much is the difference? Okay? Think about, can we go even further? Yeah, because here we only consider k equals 10. Can you consider k equals 100? When k equals 100, how big is the difference? Think about that. When k equals 100, how big is the difference? That's huge, right? Now, based on this special case, you can answer our question number 9 of quiz 1. What's the question 9 of quiz 1? If you want to answer, this one related to that. Okay? Look at this example when you answer question 9 of quiz 1. Okay? Yeah. This experiment closely related to that. Okay? All right. Yeah. So that's the first special technique for special case, monomial, special case. All right. Essence of this method. Yeah. Reuse the resource as much as we can to save operations. Here, there is a simple, good idea that is very useful in real-world applications. How do you save your resource? Reuse the resource as much as you can. What is the resource? All these intermediate results, that's your resource. Because you already use your resource to do the computation, right? Multiplication. That's also our resource we use to do the computation. So when you spend a certain number of multiplications, you don't want to waste your resource, right? So you want to reuse your resource you already have. So that's the essence of repeated squaring. Keep using your resource. Do not waste it. Do not recalculate. For example, you already have x to the 4th. Next time when you calculate x to the 8th, do not recalculate x to the 4th. You already have it. Just use it. If you do the redundant calculation, you waste your computation resource. That's the main idea here. That's the, main point we use to save our computation resource. Okay? Yeah. All right. That's this first topic. Yeah. Yeah. All right. So here, let's look at we want to, look at other special cases. If n is not any power of 2. Yeah. Because n equals power of 2, that's too special. That's too special. Okay? No. Not general enough. Now we want to consider any n, any positive integer n. Yeah. Can we use the, we just want to extend this repeated squaring a little more to save our computation resource. Yeah. Here, let me show you. Even if n is not power of 2, we can still apply the repeated squaring technique. Yeah. But definitely we need to do a little more computation. Yeah. Yeah. All right, but here, let's look at I use a simple example. N equals 217. It's not the power of 2. Okay? Yeah. But we can split it as a sum of power of 2, right? Yeah. We can represent it as a sum of power of 2 using the binary representation, right? Binary representation. Yeah. All right. So here, what is the largest power of 2 under n? Below. Yeah. Less than n. 2 to the 7th, right? 128. Yeah. Because 2 to the 8th, that is 256. That's larger than n. Yeah. All right. So the fastest way to get this monomial, x to the 128th, this monomial, the fastest way, we need 7 multiplications. Yeah, because this 2 to the k, this k is 7. Based on the result of the previous slide, we need k multiplications, 7 multiplications here. Okay. So now, reuse the resource. Let me show you how to reuse the resource. When, after we spend 7 multiplications, we want to see what are the intermediate results we already have after 7 multiplications. So we want to, that's our resource, computation resource. Okay. This list. After 7, do we get all these numbers? First multiplication, second, third, fourth, fifth, sixth, seventh. So that's all our resource, right? So all those 7 numbers, all known, okay? That means if we need to use any of the 7 expressions, we should not recalculate it, right? We just pick it from the our list, or our bank, okay, whatever you call it, our pool, all right? Yeah, computation, resource pool, we pick from there and do the multiplication. To get our goal, we want to get x to the 217th. Yeah, so, all right, so decompose the number as sum of power of 2. Decompose that 217. Yeah, 128 plus 89. 89, can we represent 89 as a sum of power of 2? So power 2 to the 6th, 25. Can we represent 25 as a sum of power of 2? 16 plus 8 plus 1. Okay, here you can see we decompose the original number 217 as the sum of power of 2. Sum of power of 2. Okay, yeah. The way we do the decomposition corresponds to the binary representation. Binary representation. Okay, yeah. All right. Now, we can do the final computation, the last round. X to the n, 217th. Now, the first number we need corresponding to this number, we can pick it from the pool, right? Yeah. Second number, x to the 64th, pick it from the pool, resource, reuse, and so on, right? X given, right? So x, also our resource. Yeah. X should be here also. Yeah. X, yeah, no multiplication needed to use x, right? No multiplication needed to use x. Yeah. Then you can see dot, 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 dot. 4 more dots, right? 4 more multiplications. Okay? That means after the 7, we need 4 more multiplications to get this final number. 7 plus 4, 11. So the answer is we need 11 multiplications to find x to the 217th, that power function. Okay, yeah. Try to get idea. Okay, yeah. Through this example, you can see any number, x to the any number, you can use it this way, right? X to the arbitrary given positive integer, because you can always write it as a binary representation, and you can write as a sum of power of 2 numbers. Then the resource, yeah, first you need to do the, generate all these numbers, put it in a pool, all right? Yeah, so then you do the final computation like that. Yeah. So this is called repeated squaring. Yeah. So we can calculate any monomial in this way, repeated squaring. Okay, yeah. That's the first technique I want to introduce. Yeah. All right. So here, as a summary, the general process. Yeah. General process. Largest case such that, yeah. See, how do we split the original given number n as the sum of power of 2? Yeah. K multiplications. Yeah. Yeah. Since if we do one more here, k plus 1, one more, that number is greater, strictly greater than n. Okay? Yeah. All right. So then we should have n should be less than or equal to 2 to the k plus 1 minus 1. Yeah. All right. So then this number, look at the expression 2 to the k plus 1 minus 1, that's greater or equal to n. That number can be represented as sum of power of 2 using all the possible power of 2 we can get on the way to calculate 2 to the k. Yeah. Because we need to do repeated squaring one by one, right? Yeah. So we generate all of, so that means the resource, the intermediate results generated like this can cover all the numbers up to this one, 2 to the k plus 1 minus 1, can cover. If your given integer is less than or equal to 2 to the k plus 1 minus 1, then we use these numbers, we can make, yeah, we can use the sum of the terms here. Sum of the terms, okay? Yeah, to get that number, to represent that number. Yeah. So here I want to say that. Yeah. Yeah. All right. So how to form x to the n? Yeah. Select elements from this pool. Okay. Yeah. So we generate the pool like that. Yeah. Yeah. So we, that's our intermediate results. Yeah. When we prepare ourselves to calculate x to the nth power. So we need to do this preparation. Yeah. All right. Yeah. So that's the whole details about repeated squaring technique. Yeah. Yeah. Similarly, yeah, after this, there is a closely related version we call repeated cubing. Squaring, then cubing. Yeah. Yeah. All right. So the next topic, yeah. So here, yeah. All right. All right. Next topic, I want to talk about repeated cubing technique. The same idea, but we just use the power of 3. Power of 3. Okay? Yeah. All right. So here, yeah, because the structure power 3 different from power of 2. Yeah. But the same idea. Let's apply the same idea. Okay? All right. So this time, I can save some time. Yeah, because we're familiar with power of 2 version. So let's just, take the same process, but using power of 3 instead of power of 2. No, that's the only difference. All right. What is the largest power of 3 under this number? Okay. 81, 2 to the 4th. Because if you calculate 2 to the 5th, 3 to the 4th. Yeah, 3 to the 4th. If you calculate 3 to the 5th, it would be greater than 217. Greater than that. So, all right. So then the fastest way to get x to the 81st, 81st, here, 8 multiplications. 8 multiplications. Can you see? Why is that? Yeah, let me show you detail here. How to get x to the 81st using 8 multiplications. All right. First round, when we calculate x cubed, we need a 2 multiplication. X times x times x. 2 dots, 2 multiplications to get x cubed, the first round. Second round, x cubed times x cubed times x cubed equals x to the 9th, 2 more multiplications to get x to the 9th. All right. Another third round, x to the 9th times x to the 9th and get x to the 27th, 2 more. All right. The last round, x to the 27th, yeah, times 2 times to get x to the 81st, 2 more multiplications. Yeah. So 2, 2, 2, 2, 2 times 4, 8 multiplications. Yeah. So we do the repeated cubing 4 times. Each time we need 2 multiplications. 2 times 4 equals 8 multiplications. Yeah. Now our resource. We use the resource. X cubed, x to the 9th, x to the 27th, x to 81st. That's our resource. Yeah. So we can use. Yeah. All right. Yeah. And we need 8 multiplications to prepare our resource intermediate results. Okay? Yeah. Yeah. All right. So the last round, decompose the number as sum of powers of 3. Powers of 3. Yeah. But we can use the coefficient 2. Yeah. Coefficient 2. 2 times, yeah. Yeah, because this term repeated twice. Yeah. Coefficient 2. Because 2 less than 3, right? If the coefficient number less than 3 base number, we can use it. Okay? Yeah. So that's the, here, we do not do the binary representation, we do the ternary representation. Base 3 representation, ternary representation, not binary. Yeah. Ternary representation, we are allowed to use coefficient 2, right? Yeah. 0, 1, 2 in ternary representation. That's the reason we can use 2. Okay? All right. Then another 2, yeah, times 27 plus 1. Okay? Yeah. So that's our ternary representation. Okay? Yeah. Sum, it's also sum of power of 3, right? Yeah, because we can use coefficient 2. Okay? Yeah. All right. Then our last representation, x to the 217, x to the 81st, this representation repeated twice. Yeah, because 2 coefficient here. Yeah. Well, you see 2, so the same term should be repeated twice. Okay. Well, you see 2 there, this x to the 27 should be repeated twice. Okay. 1 repeated once. Okay. All right. Yeah. But all these numbers come from the pool, right? Known results. They are known results. Yeah. We just put there, okay? No extra computation, right? But we need new multiplications corresponding to dot, 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 4 dots here. So 4 more multiplications. 8 preparation multiplications plus 4 new multiplications. So the total 12 multiplications. So that's the repeated cubing technique. Yeah. Okay. Yeah. Try to understand. Try to understand. Yeah. Yeah. Because in the first programming project, I asked you to implement these 2 techniques for monomial calculation. Okay? So any question so far? Yeah. All right. Yeah. Yeah. Try to understand. Okay? All right. Yeah. Which method here after that, after we learn these 2 techniques, which method, the repeated squaring or repeated cubing, performs better in general? Let me ask you this question. Which one? Yeah. If we just look at this particular example, yeah, n equals 217, repeated squaring is better, right? Remember, it's 11. We need 11. Here, 1 more, 12. 1 more, okay? Yeah. But you cannot say repeated squaring is always better than repeated cubing. You cannot say that. Okay? Because for some special n numbers, repeated squaring better, but for some other different n numbers, repeated cubing would be better. Okay? Yeah. So here, basically, so here, let me give you the idea. Basically, if the targeting number n is closer to power of 2, then repeated squaring is better. If the targeting number n is closer to power of 3, then repeated cubing is better. Okay? Yeah. If somewhere in the middle, then it's hard to say it. Okay? Somewhere in the middle, because we need to work on it. We need to work on it to see which one is better. Yeah. Okay? Yeah. All right. Yeah. Yeah. So that's those two techniques. Yeah. Then the next one, another special case. Also interesting special case I like to talk about. Take advantage of the structure of Pascal's triangle. Yeah. So another interesting special case. Yeah. So let me explain this method. Yeah. So this method, this time we consider special polynomial, non-monomial. Yeah. This time the special polynomial may have multiple terms, monomial single term. Yeah. Here, non-monomial more than one terms. Okay? Yeah, more than one terms. But the coefficients follow some special pattern. Special pattern. Okay? Yeah. Yeah. Then we can take advantage of the structure. Here, let me show you that special example. All right. One interesting thing, I don't know if you heard of this concept, Pascal's triangle, before. Yeah. 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 Some of you, yeah. So let me explain this interesting Pascal's triangle. Okay? A triangle like that, using the numbers. A diagram showing the first 8 rows of the Pascal's triangle. How do we get these numbers? Remember, binomial expansion. When we do binomial expansion, these are the coefficients for the binomial formula. Yeah. So let me give you the binomial. What's the binomial formula? When we expand, this is a binomial, only 2 terms, right? Raised to nth power, x plus y parenthesis to the nth power, we can do the expansion. Okay? Multiply out all the terms out explicitly. We need to use the combinatorial numbers as the coefficients. Yeah? When you learn the discrete math, yeah. So this part belongs to the discrete math. Yeah. Binomial coefficients, yeah, all these terms adding together. Okay, all right. Then when n equals 0, all these binomial numbers corresponds to the first row number. N equals 0, that's 1, so 1. Only one term. When n equals 1, you have 2 terms, that's binomial coefficients, 1 and 1. Okay? When n equals 3, yeah, so here, so each number, yeah, so here, yeah. Oh, this is the definition of the binomial numbers. Yeah. How do you define, combinatorial numbers? How do you define these combinatorial numbers? This is the formula for the combinatorial numbers. Okay? Yeah, all right. Yeah. Then the first row corresponds to n equals 0. N equals 0. So, yeah, that's first row. Second row corresponds to x plus y to the first. Because x coefficient is 1, y coefficient also 1. So 1 and 1. Yeah. All right. The third, x plus y, parenthesis square, if you do the binomial expansion, you get a 1 to 1, right? X squared plus 2xy plus y squared. So 1 to 1 coefficient. 1 to 1. Okay? x plus y, parenthesis, cube, the corresponding coefficient 1, 3, 3, 1, and so on. Okay? So that's the x plus 1, parenthesis to the fourth, 1, 4, 6, 4, 1. Okay? Based on the binomial expansion. Yeah. And all these numbers. Okay? All right. And this Pascal triangle has an interesting property. Okay? Look at any number. If we look at any number, it is a sum of two numbers on the line above this line, the two shoulder corresponding to the two shoulder positions. Okay? 3, 3, these two adding together 6. Those 4, 3, 1, sum of 3 and 1 is 4. So anywhere you have that property. Okay? 10 plus 10, you get 20. Okay? 15 plus 20, you get 35, and so on. Everywhere you have that property. Okay? So that's the way we define this Pascal's triangle. Okay? All right. With this special structure, now I want to ask you a new question. How many multiplications do we need to calculate this polynomial? Yeah, this is a polynomial, right? 1 plus 5x plus 10x squared plus 10x cubed plus 5x fourth plus x to the fifth. This special polynomial, this time. Okay. If you use the Horner's rule, how many multiplications do you need? If you use Horner's rule, 4 or 5? Good, 4. Because the leading coefficient is 1. So you can save one multiplication. Okay? Leading coefficient is 1. You don't need the last multiplication, so it's 4. 4. Okay? You don't need the last one. Right? Yeah. All right. Now, when we apply the Horner's rule, we need 4 multiplications. Okay? Yeah. Without leading coefficient. Leading coefficient is just 1. Okay? Yeah. All right. But now, can you see this, the coefficient's special pattern corresponds to one row in the Pascal's triangle? Can you see that? Right? Then, can we represent it as a binomial formula? Binomial formula? Okay? All right? Yeah. Based on the binomial formula here, this polynomial equals x plus 1 parenthesis to the fifth. X plus 1 parenthesis to the fifth. Okay? How many multiplications do you need to calculate this representation? Any idea? How many multiplications? 3. Can you see 3? Other students, can you see 3? Not 4. 3. Repeated squaring. Repeated squaring. All right? Yeah. Let's do first one. Because we do not look at the addition. We only look at the multiplication. The first one, parenthesis, x plus 1 times itself, x plus 1 squared. Okay? Second multiplication, x plus 1 squared times x plus 1 squared equals x plus 1 to the fourth. Second multiplication. Okay? Then the last multiplication, x plus 1 to the fourth times x plus 1 parenthesis equals x plus 1 parenthesis to the fifth. Third multiplication. See? Yeah. Although we just save 1 here, from 4 multiplications to 3 multiplications. Yeah. But, we do better than Horner's rule, right? Yeah. So here, this is a polynomial. Yeah. Polynomial. Yeah. Not a monomial, right? Yeah. Yeah. But if we take advantage of the structure of the Pascal's triangle, we can do much better. We can do much better, especially if the exponent number is large. The larger, then we can save more. The larger the exponent number is, we can save more multiplications. Okay? Yeah? Yeah. All right. So here I give you 3 special cases. Yeah. Other than the general case, Horner's rule. Here I give you 3 special cases. Yeah. Monomial. Yeah. Monomial, 2 techniques. Yeah. Then Pascal's, triangle structure. Yeah. All right. So that should be enough for this topic. Okay. For polynomial evaluation topic. So we just need, this much content. Yeah. All right. Yeah. Next, yeah, we move to part D, another interesting topic in this module 1, optimality of algorithms. Yeah. The last topic of this module, optimality of algorithms. Yeah. So after you make an algorithm, yeah, sometimes we want to consider if our algorithm is optimal or not. If it is optimal or not. Yeah. So here, I want to use a simple example to show you the optimality issue. Yeah. All right. The minimum selection problem. Our problem, computing problem number 3, find the minimum of an array. It's a simple problem, minimum of array. So everyone here, you can do it. Yeah, I believe everyone here, you can do it. Yeah. Yeah. But our main focus is not on the solution. Our main focus is on the optimality of the solution. Not the solution itself, it's on the optimality of the solution. Yeah. All right. Look at the question first. Given array with n elements, the indices, yeah, in this range. Yeah. Go find the index I such that A of I is the minimum of the array. Minimum of the array. Okay. Yeah. That's the goal. Yeah. The problem type, we call this type of problem we call a selection problem. Yeah. Yeah. So for this class, we will learn 3 basic types. Yeah. We already covered these 3 basic types. The first one, the first type, we haven't. Yeah. We covered 2 of the 3. Yeah. Yeah, the third one, our next question, we will cover the third type. Yeah. So we did a search, linear search, right? Search type. That's a basic type. Search type. Yeah. This one, selection type. The next one, sort. Sort. These 2 basic type for this class. Yeah. All right, so here I give you the reference in the textbook. Yeah. Selection problem. First, what's the selection problem? Yeah. Let me give you the definition of the selection problem. What's that? Yeah. Given array, okay? Yeah, still given array, okay? Then the goal, find the kth smallest element in a given array. Kth smallest. Yeah. And in this version, k equals 1. First, minimum is the first smallest element. Yeah. Yeah, minimum. Yeah. K equals 1, the first smallest. Yeah. Maximum, k equals n. Yeah. Nth smallest, that is the largest. Yeah. Okay? Yeah. All right. Here, let me quickly describe the solution, because solution very simple. Yeah. So let's get the solution first. Yeah. Yeah. At the beginning, we do initialization. Okay? Yeah. initial. So we need to use a main variable to store the minimum of the whole array. Yeah. But at the beginning, we store the value of the first element in this variable, the main variable. That's initialization. Yeah. After that, then the general step, we compare the value stored in this main variable and A of I goes from 1 through n minus 1. Yeah. The remaining elements. Yeah. All right. So then, two cases we need to consider. First case, if main value is greater than A of I, the current value of the current element. Okay? Then, greater than, that means the current element is less than the value stored in the main. That means we can replace the value stored in the main by the current element. We can make the value in this main variable smaller by replacement. After the replacement, the value stored in this main variable would be smaller. Okay? All right, that's the first case. Second case, otherwise, main less than or equal to, then we do not do the replacement. We keep going. Because we cannot make it smaller. We cannot make it smaller, so we keep going. Okay? We move to the next iterations. Compare main value with A of next element, I plus 1, and see if we can improve, make it smaller or not, until we reach the last element. After we compare the value in the main variable with the last element, we can return the value stored in this main variable as the function value. As this, we define a function here as the final result of this function. That's the solution. In that way, we find the minimum. Okay? Yeah. All right, so here, that's the simple implementation. Yeah. All right. Now, the question. You look at these steps. How many comparisons do we need to get a final answer based on the steps here? How many comparisons? N minus 1. Yeah. The reason is the first element, this is an assignment. This is not a comparison. Okay? So for the first element, there is no comparison needed. First element, we just do assignment. Yeah. Here, I ask you number of comparisons. You ignore assignment. Okay? So you do not count assignment operation. Yeah. So you should not include the first element. Then, after the first element, for each of the remaining elements, each one, you do one comparison. Right? So the final answer is n minus 1 comparisons. N minus 1 comparisons. For this solution, n minus 1 comparisons. Yeah. Okay? Yeah. So now the question. Yeah. As I said at the beginning, the solution is easy. Our main focus is on the optimality of the solution. It's not on the solution itself. We want to see if this solution is the best or not. If this solution can be improved or not. We want to see that. Can you do better than this one? Can you do better than this one? Better than n minus 1? For example, can you do n minus 2 comparisons? N minus 2 comparisons to solve this problem? Yeah. That's the question of our Question 10 of quiz 1. I ask you if it's possible to use n-2 comparisons to solve this problem. Question 10 of quiz 1. Okay? Yeah. All right. So let me finish the story. Then you can answer question 10 of quiz 1. Okay? Yeah. All right. So next, how to see it. So here. How to see if this is a best solution or not. Optimality. How to see the optimality of the solution. Yeah. All right. All right, yeah. So assignment for the first one. So we do not treat it as a comparison. Yeah, we only count comparison. Counting by reference. Yeah. So because for the remaining n-1 elements, we make one-to-one correspondence. Each element, there is one comparison, one-to-one correspondence. So that's our counting by reference technique. So we get this number. All right, so here, review this counting by reference another time, this technique another time. Yeah. All right. All right. One comparison corresponds to one element. Okay. Skip the first element. Yeah. Index 0 element, there is no comparison. We skip it. Yeah. But for the remaining n-1 elements, we have the one-to-one correspondence. So we have this n-1 answer. Yeah. Yeah. All right. Next, optimality. The question. Is it possible to further improve the algorithm? Further improve. Yeah. If it's possible, then that means the previous solution is not optimal, because we can further improve it. Yeah. Otherwise, if it's optimal, nobody can further improve it. Because it's optimal, nobody can further improve it. So we want to answer this important question. Yeah. All right.
We're assuming that the array is not sorted already, right?
Array not sorted, or
we're assuming that the array isn't already sorted.
not ordered, correct. Yeah, not ordered. Yeah. Good point. Yeah, not ordered, unordered. Yeah, good. If we do not mention, yeah, here, if we do not say anything, we assume unordered. Yeah. Because you cannot assume ordered. Yeah? Yeah. Nobody can assume given array is ordered. Yeah. You have to see the word ordered array clearly. Then you can use that information. Otherwise, you cannot use that information. Yeah. That's simple. Okay. The first option, two options. First one, we want to improve the algorithm. We always want to improve the given algorithm. But we may not be able to do that. Yeah. Many times, we may not be able to improve the current algorithm. Yeah. So then we take the second option. Convince people that it is already optimal. Yeah. So we have another option. If we cannot improve it, we may try to convince people it is already optimal. Yeah. So then, we do not need to do anything, right? Already optimal. The best we can get. Yeah. All right, so here, we want to try the second option. Because the first one, we don't know how to improve it. Nobody knows how to improve it. Right? Yeah. So the first option, too hard. So now we want to try the second option. Yeah. All right. Right? Post-solution thinking. Yeah. After we find a solution of the computing problem, post-solution thinking, we should try to improve the solution as much as we can. Yeah. For this class, we will do that. Okay? After we find a solution, so we want to see, can we improve it? Yeah. All right. The solution may have been optimal already. Yeah. Sometimes it's optimal, so then we can stop. Yeah. All right. Yeah. So optimality here. Now, let me explain the optimality concept here. Okay. So what's the optimality? Yeah. So here, in order to convince people the current algorithm is already optimal, it is pretty hard. It is pretty hard. Yeah. The hard part. Because we need to consider all the possible algorithm that solve the selection problem. We need to cover all the possible such algorithms, right? Yeah. If you miss even one possible algorithm, you may miss the best one, right? Logically, you may miss the best one if you couldn't cover all possible such algorithms. Yeah. So that's the hard part, because we need to cover all the possible algorithms and show that this one is optimal. That's hard. Yeah. All right. Question. How do you, yeah, because among all the possible, there are many unknown algorithms, right? Yeah. Unknown. Yeah. Because you cannot exhaust all the possible algorithms, right? Nobody can exhaust all the possible algorithms that solve this problem, given computing problem. Okay? That means there are many unknown algorithms. Unknown. Okay? The question, how do you study unknown algorithms? Those algorithms are unknown. But how do you study unknown algorithms? Is it hard? Unknown algorithms. You do not know the details. How can you study those algorithms without knowing the details of those algorithms? Is that possible? The question is that possible? You can study unknown algorithms?
Probably depends on the conclusion we want to get to. So maybe rather than studying details, study the conclusion.
Yeah. Idea related. Yeah. So let me say in this way. Yeah. Is it possible? The answer is yes. It's possible to study unknown algorithms. How? How to study unknown algorithms? How to study unknown algorithms? Yeah. If we can discover some common property or properties for all those algorithms, if you can discover, although unknown, we don't know the details, but if we're lucky, we can discover some uncommon property or properties, yeah, that all unknown algorithms should satisfy. Then we can use the common property to study unknown algorithms. Here we are lucky. We can find a common property to cover all those possible algorithms. Yeah, yeah. I will show you that. Common properties. Okay? All right. Yeah. All right. So let me finish this slide, then we take a break. Yeah. Finish this slide. Okay. All right. Now, the question, how to convince people that our algorithm is optimal. Here, we need some imagination based on our real world experience. When we convince people, we use the common experience everyone has in our real world experience. Yeah. So we use that to help people understand. Yeah. All right. So what's that? The experience playing sports games. Playing sports games. Everyone has this experience, right? Yeah. Playing sports games. Okay. The tournament method. All right. Yeah. Many different methods people play sports games. Yeah. Here we use analogy. Okay. So our experience from real world sports games. Yeah. All right. when we do comparison, we compare two numbers and see which one is greater, which one is smaller. Can we make the similar analogy as in a sports game or match? Two players play in a match between two players, one winner, one loser. Can we use that analogy, right? The winner you can interpret as greater or less, right? You can choose. Yeah, here. Yeah. The results. Yeah, let's look at the results. Less than. Yeah, because here our goal, we want to find the minimum. Minimum means the smaller the better, right? Minimum means the smaller the better. So we want to make the smaller one the winner. How about that? Because we want to select the smaller one. Yeah. Otherwise, if we want to find the maximum, then the larger the better. Then we make it greater the winner. Yeah. Here, smaller the winner. Okay? Because we want to find the minimum. Okay? All right. So one number is less than the other number, then we interpret it as a win. The less one is a win. If we do the comparison. Okay? Comparison. Equal, it's a tie. Greater than, lose. Okay? Yeah. Loss. Okay? Yeah. All right? Yeah. Then, but here, in our comparison, there is one arithmetic property we need to use. Transitivity, algebra property. Yeah. Algebra property. Transitivity property. In the real world sports game, no such property. Yeah. But here we have such property. Transitivity, what's that? If PA greater than PB, player A greater than player B, and the PB greater than PC, by the transitivity, PA is greater than PC. That's the transitivity property. Yeah. But in the sports game, we don't have that, right? The sports game, player A beats player B, and the player B beats player C. You cannot say player A beats player C, right? Yeah. Player A may lose to player C in real world. Yeah. So this part, it's different. Here we have this property. Yeah. All right. So here, because when we use the transitivity property, we allow indirect comparison. Indirect comparison. So what's that? Here, if PA greater than PB and the PB greater than PC, we already know PA greater than PC. We do not need to do comparison directly, right? So we can save one comparison between PA and the PC. So we call in PA beats PC in an indirect comparison. It's not direct comparison. We do not need to do direct comparison. We use the transitivity. The transitivity property gives us indirect comparison between PA and a PC. Yeah. Yeah. So that's the special thing. All right. So now, convincing argument. After we understand the environment, so I just explained the environment. Next, I can make a convincing argument. Let's take a break. After the break, let me go through a list of arguments to convince you. Yeah. Because it takes some time to understand. Yeah. All right, so let's, when you come back at 7, we finish this convincing argument.